Good morning. Myself, Dr. B. Lambardi, Associate Professor, Department of Artificial Intelligence and Data Science, Ramco Institute of Technology. Good morning. Today we are going to discuss about the topic distributed mutual exclusion. Before entering into the topic, you must know about what is distributed systems. A distributed system is a collection of computer programs that utilize computational resources across multiple separate computational nodes to achieve a common shared goal. The particular goal is achieved by means of passing messages. In other terms, we say that a distributed system is a collection of components on different networked computers that work together to achieve a common goal. So next, we are going to know about what is distributed mutual exclusion. Distributed mutual exclusion is it refers to ensuring that only one process or node can access a shared resource at the same time, which is generally used to prevent conflicts when multiple processes try to modify the same data simultaneously. For example, if you're having a file contains read and write access. So if you are going to read the particular file, more than one user can read the file at the same time. But if you are going to write a single file, write something in a single file, only one user can access the particular file. So that's what mutual exclusion was done. For example, a distributed database contains where it contains multiple servers which need to update a shared record. It requires a mechanism to ensure only one server can write to that record at a time. Just it preventing inconsistent data updates. So mutual exclusion generally used to prevent inconsistent data updates. For example, if you take the example of online railway ticket booking system, where multiple users can book a ticket from different locations. If suppose, for example, if, only last available seat in a train is going to book, the system must ensure that only one user gets the seat. It will avoid double booking or multiple booking. So it can be achieved only through mutual exclusion. But in distributed system, mutual exclusion is a fundamental problem. Because more than one user can access a single data. So mutual exclusion ensures that concurrent access of process to a shared resource or data is serialized. That is, the particular data will be accessed in a or executed in a mutually exclusive manner. Mutual exclusion in a distributed system states that only one process is allowed to execute or enter into a critical section region at a given time. Uh, so in generally, it will be achieved by means of shared variables or semaphores, or we are using maybe they are using a local kernel to implement mutual exclusion. But it cannot. But here in distributed system, it does not support shared variables or semaphore or local kernel. So it cannot be used to implement that particular technology in implementing mutual exclusion in distributed system, right? So the only way of implementing mutual exclusion in distributed system is message passing. By message passing only, we are going to implement or we are going to achieve distributed mutual exclusion. So, for example, if you're having three process or five process, if any process wants to enter into a critical section region, they have to pass a request message to all the process present in the system. If every process, if the particular process getting permission from all the process, then only they have to enter into a critical section region. Otherwise, they have to wait. They cannot enter into critical section region. They have to wait for the reply from all other processes. Uh, the design of distributed mutual exclusion algorithm is really complex because the algorithm we are going to design for distributed mutual exclusion is going to deal with unpredictable message delays, and they doesn't know about the complete knowledge of the system state. So there are three basic approaches for implementing distributed mutual exclusion algorithm. One is token-based approach, and the non-token-based approach, and the final is quorum-based approach. So first one is token-based approach. If any process wants to enter into a critical section region, they have to if the particular process having the token, they have a rights to enter into a critical section region. So for that, they have to send a request message to all the processes present in the system. If any process having the token, they have to send a token to the particular process. For that purpose, a unique token is shared among all the sites. If a site possesses a unique token, the particular process is allowed to enter into a critical section region. So generally, for achieving this token-based approach, here we are going to use a sequence number to order requests for the critical section. For every request, the system will allocate a sequence number. Based on the sequence number only, they have to enter into a critical section region. For each request for critical section region, it contains a sequence number. The particular sequence number concept is used to distinguish old and current requests. That is, we have to give permission only to the recent requests or current requests. So this approach ensures mutual exclusion as a token is unique, because if only one process is going to get a token, that particular if the process having the token, they have only the rights to enter into critical section region. So it ensures mutual exclusion. The example in our syllabus, the example for token-based approach is Suzuki Kasami's broadcast algorithm. And the next one is non-token based approach. Here there is no token concepts. So if any site or if any process wants to enter into a critical section region, they have to send a request message to all the process present in the system. If it receives the reply from all the other process, then only they have to enter into a critical section region. So if any site wants to communicate with other sites, they have to if any site wants to enter into critical section region, they have to send a request message to all the process. If all the process reply only, they have to enter into a critical section region. Otherwise, they can't enter into a critical section region. Here they are going to use timestamp instead of sequence number. So lower the timestamp, higher the priority. If all algorithm which follows non-token based approach maintains a logical clock, so the logical clocks will be updated by means of Lampard scheme. In our syllabus, the non-token based approach algorithm is Lampard's algorithm and Ricard Agarwala's algorithm. And the final one is quorum based approach. So instead of requesting permission to execute a critical section region from all other sites, here they are going to separate a subset of sites, which is called a quorum. If any two subsets of sites or quorum contains a common site, this common site is responsible to ensure mutual exclusion algorithm. So it depends upon the subset size, reply will be received. So based on that reply, the particular site or particular processes have a right to enter into a critical section region. Here, the example is Merkava's algorithm. Before seeing the topic, how we are going to model our system. Generally, the system consists of n sites. So without loss of generality, we do some assumptions. Here, what we are going to assume is that a single process is running on each site. So if we consider a single site, only a single process is running on each and every site for assumption only. So for example, if process at site SI is denoted by PI, so all these processes communicate asynchronously over an underlying communication network. So if any process wishing to enter into a critical section region, they have to request all other process or all the subset of process by sending a request message. And by sending a request, after sending a request message, they have to wait for the reply from all other sites to enter into a critical section region. Once they get a reply from all other process, then only they are going to enter the particular process or particular site is going to enter into a critical section region. So if suppose if any of the process is already sent a request message, they are in a waiting state. They are not allowed to make further request to enter the critical section region. So if they are already sent a request message, after getting a reply from the particular cycle, then only they have to enter into critical section. After that only they have to send a second request. At the time of waiting for reply from all the process, they cannot send a they cannot send another request. So generally, the particular site or particular process is in three states only. One is maybe they are requesting the critical section, or maybe they are executing the critical section, or neither requesting or nor executing the critical section. That is the particular site or particular process in a idle state. In the in at the time of requesting the requesting the critical section state, the site is the site is blacked and cannot make further requests for the critical section. As already said, if the particular site or particular process requesting the critical section, they cannot and waiting for the reply, they cannot send further requests for to enter into a critical section region. Once the cycle completes, then only they have to send another request message. If suppose if the state is in ideal, if the particular site or particular process in ideal state, the site is executing outside the critical. Maybe they are in ideal state, or they are maybe executing some of the process, some of the data, or some of the job which is done outside the critical section region. That does not matter for this task. In the token-based algorithm, a site can also be in a state where a site holding the token is executing outside the critical section. Such state is referred to as ideal state. For example, if the particular process or particular site is having the token, but they doesn't need they doesn't want to enter into critical section region. Maybe they have to work on some other outside. That is, they have to work on outside the critical section region. That is possible, and that particular state is called ideal token state. And at any instant, a site may have several pending requests for critical section. Uh, at that point of time, the site may queue up these requests and serve them at one at a time. So only one process is entered into a critical section region. Maybe they are going to use some queuing technique, or timestamp value, or the latest sequence number technique. They have to give access to the particular sets. So again, here we are going to assume another one technique. We assume that channels reliably deliver all messages. So if the communication here, what we are going to assume is that all the communication channels are reliable, and all the communication channels are deliver all the messages reliably. And in there is no any other crash, and there is no uh, network partition. So some mutual exclusion algorithms are designed to handle such situations. So here, but in here we are going to discuss. Here we are going to assume the above techniques only. So generally, many of the algorithms are used for many of the algorithms are used Lampard style logical chains to assign a timestamp value. So timestamps are used to decide the priority of requests in case of conflict. The general rule followed here is the smaller the timestamp, higher the priority. So the timestamp, if the timestamp value is smaller, it contains higher priority to enter into the critical section region for each and every sites. Right. So the main requirements of mutual exclusion algorithms. So mutual exclusion algorithms have some properties. That is, there are three important properties are there. One is safety property, and the liveness property, and another one is the fairness property. First one is we are going to see about the safety property. Safety property states that at any instant or at any given time, only one process can execute the critical section. So this is an essential property of a mutual exclusion algorithm. So safety property states that at any instant or any particular time, only one process is allowed to execute a critical section region at a single time or at a same time. So this is a very, very essential property. So whatever algorithm you are going to propose for mutual exclusion, so you must satisfy the safety property. And the second one is liveness property. This property mainly focus on the absence of deadlock and starness. So two or more sites should not endlessly wait for messages that will never arrive. So here, the particular algorithm must ensure that there is no deadlock will occur. There is the absence of deadlock, and they are going to in addition, a site must not wait indefinitely to execute the critical section while other sites are repeatedly executing the critical section. So here we are going to give equal priority to all the sites or all the process present in the system. There is no bias or there is no conflict in your algorithms. So the liveness property ensures that particular uh, concepts. Next one is fairness property. So fairness property in the context of mutual exclusion algorithm means that each process get a fair chance to execute the critical section region. So if maybe any if they are giving any priority any technique they are going to follow, they are if they are going to give a fair chance to execute the critical section for all the sites or all the process. So generally, as already said, the time is determined by a logical clock. Uh, uh, that's all about the requirements of mutual exclusion algorithm. The first property, that is safety properties, is very, very important, and it's must or necessary for to implement mutual exclusion algorithm. The other two properties are considered important in mutual exclusion algorithm. So if you are going to implement any mutual exclusion algorithms, so you must satisfy the safety property, and as far as liveness and fairness property. So it's your algorithm going to you must consider that particular algorithm, right? Performance metrics. So there are four performance metrics are there. One is message complexity, synchronization delay, response time, and system throughput. First one is message complexity. So this is only purely based on the number of messages that are required to enter into a critical section region for the particular site. So if suppose, for example, if you are taking Ricardo Agarwala's algorithm, they are in need of only two messages. That is, they are having only request message and reply message. But in case of Lampart's algorithm, if we are going to use request, reply, and release message. So this is what the difference. The number of messages that are required for the critical section to execute by a particular site is a message complexity, and the next one is synchronization delay. After one site leaves from the critical section, it is the time required and before the next site enter the critical section. The time difference between the one site leaving the critical section and another site enter into the critical section is called a synchronization delay. And the next one is response time. This is a time interval a request wait for its critical section execution to be over after its request messages have been sent out. So initially they are going to send a request message and they have to wait for the reply. So after that they have to wait for to enter into critical section region. Once they have to enter into critical section region and then they have to exit from the critical section. The whole time is called a response time. Next one is system throughput. The formula for system throughput is 1 divided by SD plus E. SD is synchronization delay, and E is average critical section execution time for all the sites present in the systems. So that's all about the distributed mutual exclusion algorithm. At the conclusion, distributed mutual exclusion algorithm is a major problem in distributed system. So we must focus, we must address the particular issue. For that, here we are going to use three approaches. One is token-based approach, non-token-based approach, and quorum-based approach. If token-based approach in the sense, if any process having the token, they have rights to enter into a critical section region. Non-token-based approach is generally done by means of message passing. If any process wants to enter into a critical section region, we have to send a request message to all the process present in the system. if reply comes from all the process, then only they have to have a rights to enter into critical section region. Here the timestamp value used, and in token based approach they are going to use a sequence number concept. Here in non-token based approach they are going to use a timestamp value, and the quorum based approach is the sites are generally linked as a subsets. If instead of getting reply from all the or all the process or all the sites present in the system, only subset will send a reply message. So this is a non-token based approach, and we have to see something about the requirements of mutual exclusion algorithm. There are three requirements: safety property, liveness property, and fairness property. In that, safety properties must are necessary, and the remaining two is liveness property and fairness property. And what if you are going to implement a mutual exclusion algorithm, you have to consider these three properties. And the performance based performance metrics is message complexity, synchronization, delay, response time, and system throughput. That's all about distributed mutual exclusion algorithm. In the next class, we are going to discuss something about the mutual exclusion algorithms. Thank you.